Differentiability. Here is the definition. The function f is said to be differentiable. That means derivative exists at the point x0 if the following limit exists. Okay, that's just the definition. But the x is now a particular point x0. If this limit exists, then we say the function is differentiable at the point x0. Okay, and we denote this by f prime at x0. Okay, which is called the derivative of f, the function f, at the point x0. Okay, and geometrically the derivative at the point gives us the slope of a tangent line at this particular point. Okay, derivative means slope of the tangent line. Conceptually, it represents an instantaneous rate of change. So slope of tangent line geometrically, but in conceptually it's the rate of change. Now in this section we want to explore three main reasons that a function is not differentiable at a point. Okay, those three cases are discontinuities. That means if the function is not continuous at that point, then the function is not differentiable at that point. Corner point, the function is continuous, but there is a corner point, corner point or cusp, then the function is not differentiable at that point. And vertical tangent line. Okay, when we draw a tangent line, if it is a vertical line, then the derivative does not exist. So here's a theorem. If the function is differentiable at a point, that means the function will be continuous at that point x0. Okay, all that means differentiability implies continuity. So differentiability is stronger. It needs a lot of things. Continuity does not need that many. That means differentiability implies continuity. So if a function is differentiable at a point, then it's continuous there. But the backward is not true. Okay, if the function, okay, backward, this is the backward corollary. If the function is not continuous, then not differentiable. Okay, and f is continuous at x0 does not mean, okay, it does not apply. It can be, but it most of the time it may not be. F is differentiable. Okay, the continuity at a point is not enough. Okay, so let me show you by graph a couple of cases where the function is not differentiable. So the first one we said discontinuity. If the function is not continuous, then obviously not differentiable. Like we can have jump discontinuity like this, okay, at this point A. Okay, this function has a jump here. That means f, this function, let's say f, this function is not continuous at A. All that means f prime at A does not exist. The function is discontinuous because the function is discontinuous at A. Or we can have some type of infinite discontinuity. It's going here at some value A, going here, same thing. The derivative at A does not exist because we have infinite discontinuity. And sometimes we can have removable discontinuity like here. Okay, that's the hole in the graph. That means derivative at this point A does not exist. So if the function is not continuous, it's not differentiable. Sometimes the function is continuous, but the function has corner point. Okay, and when the function has a corner point at some point, then the function is not differentiable. Like here, okay, this function is continuous. Okay, but here at a, the derivative at a does not exist. If this function is, let's say f prime a does not exist, but this is continuous though. The function is continuous, but it's not differentiable. Sometimes we can have some type of cusp. It's the corner point, okay, but it's even sharp. Derivative does not exist. And for this we can show, look, we know the graph of the absolute value of x, which is just a V-shaped graph. Okay, this is the graph of absolute value of x, and at 0 we have a corner point, then the derivative does not exist. Okay, f prime at 0 does not exist. So I want to prove this here. Let me show you this. So the definition of derivative is f prime at any point x is given by the definition f of x plus h minus f of x over h, and we let that h be 0. Now we want to find at 0, the particular point 0. So this value is 0. So we can find, just replace everywhere 0. Okay, that was the derivative at any point x, but now our x is 0, so I'm writing in this way, which is, let me define this, h going to 0. This is f of h, in fact, minus f of 0 over h. That is, in our case, f of h. Look, f of x is absolute x. That means f of h is just absolute h. When we have input x, we have output absolute x. So input h means output absolute h, minus f of 0. So f at 0 means absolute 0, which is 0, over h. Now let's find this limit. In fact, minus 0 doesn't count, absolute h over h. And we know that whenever absolute value is included, when this is involved, to evaluate this limit, we have to take one-sided limit. Okay, to evaluate this limit, we find one-sided limit. So limit when h goes to 0 from left of this fraction, and let me write here, limit of the same thing when h goes to 0 from right side. Okay, so when h goes to 0 from left side means h is less than 0. In fact, h is negative. Okay, that's negative h. Then absolute value of h will be negative h, because h is negative in this case. This is negative, and when we put negative sign in front, whole thing becomes positive over h. H cancel, so negative 1. Okay, so this limit is negative 1. Left hand limit of this is negative 1. In the same way, let's find right hand limit. H is going approaching to 0 from right side, means h is bigger than 0. That means h is positive. So when h is positive, absolute value of h is just h. Just h over h, they cancel, so 1. So the left hand limit is negative 1 and the right hand limit is 1. That means this limit does not exist. Okay, because we tried, we looked from both sides and they are different. This limit does not exist means from the definition we don't have derivative at 0. Okay, so I was just trying to justify at corner point the function is continuous, because we can graph without lifting our pen out of paper. The function is continuous, but when we have a corner point, the function is not differentiable. Okay, so far we've seen two cases. A function is not continuous. If the function is not continuous, then the function is not differentiable. If the function has a corner point, then it's not differentiable. And if we go up all the way, discontinuities, corner point, and third part is vertical tangent line. Sometimes we can have vertical tangent line. That's kind of rare, but in that case, the function is not differentiable. Okay, vertical tangent line. Okay, vertical tangent line. When we graph a function, let's say something like this, we have like something like this graph, and at this point here, A, if we try to draw a tangent line at A, then this will be a vertical line. Okay, that means the derivative at A does not exist because the slope of vertical line is undefined. That's the whole reason. So when we have a vertical tangent line, then the derivative does not exist. Okay, let me show you another graph here. Okay, this is the graph of function y equals cube root of x. Okay, when we graph this function at 0, okay, so we have something similar to this. Look at this graph. And if we try to draw a tangent line at 0, then the tangent line will be a vertical line. So this function has a vertical tangent line at 0. So the derivative of this function, if we say f or y something, f prime at 0 does not exist. Okay, final.